We have practiced taking the derivative of a natural logarithm, and today we're going to differentiate using logarithm rules from our pre-calculus classes. So today we talk about something called logarithmic differentiation. And so logarithmic differentiation sounds like a tough concept, but the idea is intended to simplify, we're going to make things simpler, a complicated problem into something relatively simple. So even though the phrase may have you looking like a confused James Corden, the technique can be helpful. So let's think about logarithmic, means using logs, and differentiation means taking the derivative. So we're going to use logarithms to help us take the derivative, and I'll show you what I mean. Example 1, find the derivative. All right, cool. I've got y equals x minus 2 squared divided by the square root of x squared plus 1. So putting this all in parentheses, I'm going to take the derivative with respect to x. The left side will just be dy dx. Then on the right side, I'm going to need the quotient rule. So I'm going to have low d high, which actually uses the chain rule, minus high d low. Ooh, I'm going to run out of room already. Negative 1/2 times 2x all over low squared. Oh, good. This looks a little bit simpler. When you square the square root, cancels out. All right, so thinking about cleaning this up a little bit, I get dy dx equals the square root of x squared plus 1 times 2x minus 4 minus x minus 2 squared. These 2's are going to cancel out. I get a x squared and x squared. I still have an x in the numerator, all over x squared plus 1. If I wanted to clean up even more, I could figure out how to put this thing to the bottom, but it would only be on this term, not on this term. So realistically, I'd have to do a lot more work. Oy. Square root of x squared plus 1 times 2x minus 4 over x squared plus 1 minus x minus 2 squared over x squared plus 1. This then would go down there, so becomes a all to the first, and then times the half becomes to the 3/2, and oi. There's my derivative, trying to get it to match for a nice multiple choice answer. Yikes. Overall, quotient rule. Okay. Well, let's think about another way we could do this. We're supposed to be focused on logarithmic differentiation. Well, I don't have any logarithms in here, so I'm going to introduce them. I'm going to take the natural log of y, and I'm going to take the natural log of this whole side. I'm just going to rewrite this as x squared plus 1 to the 1/2. Well, using properties of logarithms then, this becomes the natural log of x minus 2 squared minus the natural log of x squared plus 1 to the 1/2, because my division can turn into subtraction. Still using properties of logs, I can swing that 2 down in front. I can swing that 1/2 down in front. And now I've done the logarithmic part. Now let's do the differentiation part, taking the derivative with respect to x. Well, the derivative of the natural log of an argument is 1 over the argument times the derivative of the argument with respect to x. 2 is a constant, it's just going to hang out. The natural log of x minus 2 is 1 over the argument times the derivative of the argument, minus 1/2 just hangs out. The natural log of x squared plus 1, its derivative will be 1 over the argument times the derivative of the argument. Well, that calculus was a lot nicer, wasn't it? Let's clean up a little bit. I have 1 over y dy dx equals, I get a 2 in the numerator here, x minus 2, and here my 2's will cancel out, minus x over x squared plus 1. So I'm really close. I'm just supposed to isolate this dy dx, which means I need to multiply both sides by y. Okay, I'm running out of room. Hopefully you guys wrote small in your notes packet. I get a dy dx equals 2 over x minus 2 minus x over x squared plus 1 times, what was y equal to again? Well, that's right. It was equal to this mess up here. X minus 2 squared over the square root of x squared plus 1. Interesting. Here's a new way of viewing my derivative. All right, so what I did is I took my derivative from number 1, cut and paste it, and my derivative from number 2. And if you were to go through and actually distribute this in, you will end up with this. So mathematically they are the same. What advantages does logarithmic differentiation provide? It does more of the cleanup work early, right, to then make the derivative nicer. So the derivative gets simplified. Okay, so taking the derivative becomes a lot nicer. Believe it or not, logarithmic differentiation, using logs to take the derivative, is not just a convenient skill to have. There are some problems that will require logarithmic differentiation because everything else fails. Let's think about when we would have to use logarithmic differentiation. Oh look, example 3. Taking the derivative of the cosine of x raised to x to the third plus 5. So if I had y equals cosine of x to the x to the third plus 5. Well, is this exponential, where the variable is in the exponent? Or is this a power function, where the variable is in the base? Weird. I've got a variable in the exponent, and I have a variable in the base, which means that this is C. Neither. You are correct. So an example of an exponential function is e to the x, or 2 to the x, or 7 to the tangent of x, where there's a number in the base and a variable in the exponent. An example of a power function would be something like x to the e, or x squared, or tangent of x to the 7th, where there's a variable raised to a number. So let's see how logarithmic differentiation can help us with the derivative at hand. So bad. All right, so I'm going to call this y equals cosine of x, x to the third plus 5. Well, logarithmic differentiation means I need a logarithm. Great, let me introduce the logarithm. I'm going to take the natural log of both sides. And I'm going to use my log property of swinging down. I'm just jumping over here so I have a little more room to write. Swinging down this exponent in front. X to the third plus 5 times the natural log of the cosine of x. Now, I no longer have an exponential variable. I no longer have a function raised to a function, right? What I can do now is take the derivative with respect to x. So the natural log of y, the derivative would be 1 over the argument times the derivative of the argument with respect to x. Here I have a product rule. First times the derivative of the natural log of an argument is 1 over the argument times the derivative of the argument plus the second times the derivative of the first. Okay, so again, product rule is coming into play here. I no longer have this weird power exponential combined function. I can turn this into a product rule by introducing logarithms into my differentiation. Let me move this down. So we need to get dy dx all by itself. That's our last step. So I'm going to multiply both sides by y. dy dx equals, big parentheses, x to the third plus 5 times, ready for this, negative tangent of x, because sine over cosine gets me tangent, plus 3x squared, I'm just writing that in front for convenience sake, the natural log of cosine, all times y, so I multiplied both sides by y, but what was y equal to? Oh, that's right, y was that bizarre function of cosine of x to the x to the third plus 5. So, final answer is this guy here. When must you use logarithmic differentiation? Must use. When you have a function raised to another function. Okay? When can you use logarithmic differentiation? You can use it to, I'm going to say, avoid a mess. Right? You can use it like on those first examples of expanding out with properties of logs so that your derivative becomes nicer. But it's when you have some sort of a variable to another variable that you have to use logarithmic differentiation. It's the only way that you can get that function out of the exponent down in front so that you can use the product rule. If you would like, write the steps to logarithmic differentiation here. So, step 1. Natural log of both sides. Number 2, apply log properties, as many as you can. Number 3, take the derivative with respect to x. Be mindful of the arguments. Number 4, isolate dy dx. We're going to have a little bit of implicit differentiation going on in there as well. That's it. Your homework is in your textbook. Logarithms, keep practicing. Again, remember, you have to use it. Logarithmic differentiation, logs to take the derivative. Have to when you have a function to a function. Can to avoid a mess. And suggested that you avoid a mess, but that's up to you. But if you ever see a function raised to a function, a variable raised to a variable, a weird combination of power and exponential, use logarithmic differentiation. You have to.